You probably do it, I don't know, 100 times a day without even thinking about it. You click a link, and poof, the internet just shows up. But what actually happens in that tiny little split second? Well, today we're going to pull back the curtain and follow the secret journey your data takes, from your keyboard, out to the cloud, and all the way back again, literally in the blink of an eye. Right? You click a link, a web page appears, it feels like absolute magic. But of course, it's not. It's actually this incredibly precise, choreographed dance of signals and protocols. And to really get our heads around how it all works, we've got to start right where the whole journey begins, inside your own home. So, let's talk about section 1. The journey kicks off right here, inside your own private digital world. This is your local area network, or LAN for short. The best way to think about it, it's your digital house. So, what is a LAN? Well, it's basically just all of your devices. Your laptop, your phone, maybe a smart TV, your gaming console, all connected together in one spot. And just like a family living in a house, they can all talk directly to each other without ever having to go outside onto the big public internet. And this diagram, it really shows this idea perfectly. It's like you've got two different worlds. On one side, you've got your private network with all your personal stuff, and on the other side, there's the massive public internet. The thing standing in the middle, acting as the gateway or maybe the security guard between those two worlds, that's your router. Okay, so now we're moving on to the next part, making the request. Your device is all set up inside its digital house, right? But before it can just venture out into the wild internet, it's got to get a few things in order. It needs to prepare for the trip, and that starts with making a formal request. Think about it. The instant your phone connects to Wi-Fi, it needs an address. Otherwise, how could it send or receive anything? This is where a little hero called DHCP comes in. DHCP, that stands for Dynamic Host Configuration Protocol, and it basically acts like your network's rental agent. It zaps a temporary, local IP address over to your device, so it has a valid return address for its big journey online. All right, so your device has its own local address. Check. But now it means the address of where it's going. We, as humans, love easy names like google.com, right? But computers, they don't speak that language. They only understand numbers. So that's where the DNS, or domain name system, steps in. You can think of it as the internet's giant phone book. It does one crucial job: translating that human-friendly name into the computer-friendly IP address that networks actually use. Okay, let's take stock. Our little data packet now has a return address and a destination address. It's all packed and ready to go. But its first big challenge isn't out on the internet. It's navigating the internal roads of your local network. This is the journey inside the house. Now, to really get this internal journey, you have to understand a key concept. Every device actually has two different kinds of addresses. You've got the IP address, which is kind of like a temporary mailing address. It can change depending on what network you're on. But then you have the MAC address. Think of that like a permanent social security number for the device, something that's literally burned into the hardware. And that's the address that's used for that final local delivery from one device to another inside your network. And this is where that MAC address becomes absolutely critical. See, when your computer sends data, it doesn't just shout it out to every other device in the house. No, it sends it to a network switch. The switch is the smart traffic cop here. It reads the destination MAC address, looks at its internal map, and says, that device is plugged into port number 5. Then it creates a direct private line just to that device. It's the difference between making a private phone call versus yelling across a crowded room. So now let's move on. Our data has made it through the local network. It's arrived at the router, the digital front door. Now, it's time to step outside, cross the border, and head into the big, wide world of the WAN. So what's a WAN? A wide area network. It's basically the opposite of your LAN. It's the enormous, sprawling network that connects all those individual digital houses together across cities, countries, and even continents. And the internet we all use every single day? Well, that's just the biggest WAN there is. But hold on, here's a puzzle for you. You might have, 10, 15 devices at home, phones, laptops, TVs, but your internet provider only gives you one public IP address. How on earth does that work? Well, the magic behind this is a process called NAT, which stands for Network Address Translation. Your router is the gatekeeper here. It takes all the requests from your private devices, sends them out using that one public IP, and then, this is the clever part, it keeps a detailed log, so when the responses come back, it knows exactly which device to send them to.
It's not just efficient, it's also a huge security feature, because it keeps your private device addresses hidden from the public internet. All right, next up, the world of Wi-Fi. Because let's be honest, for most of us, this isn't happening over a clunky physical cable anymore, right? All this data is flying invisibly through the air. So we absolutely have to take a quick detour and talk about how Wi-Fi actually works.
So you've definitely seen terms like Wi-Fi 6 thrown around. The technical name for the standard is actually 802.11, and its evolution has been, well, it's just staggering. I mean, we started out with a standard that could handle just 11 megabits per second. Fast forward to today with Wi-Fi 6 and now Wi-Fi 7, and we're talking about speeds in the tens of gigabits per second. That's powerful enough to support an entire stadium full of people all streaming video at once. Just incredible. Now, if you look at your Wi-Fi options, you probably see two networks from your router, right? One is 2.4 gigahertz, the other is 5 gigahertz. What's the deal with that? Well, it all comes down to a really simple trade-off. If you only remember one thing, remember this: low goes far, high goes fast. The lower 2.4 gigahertz frequency is great at punching through walls and going long distances, but it's slower. The higher 5 gigahertz frequency is way, way faster, but its signal doesn't travel as far and gets blocked by walls more easily.
And this image right here shows you exactly why that 2.4 gigahertz band can get so slow and crowded. Just look at all that overlap between the channels. In reality, there are only 3 channels, 1, 6, and 11, that don't interfere with each other. So if your Wi-Fi and your neighbor's Wi-Fi and the neighbor next to them are all trying to talk on this tiny, crowded highway, yeah, everything grinds to a halt.
Okay, we are in the home stretch now. Our little data packet has traveled across the entire internet and has arrived at the correct server. But there are still 2 huge questions left. First, how does the server know which specific application, the web server, the email server, should get this data? And second, how did it stay safe from snoops and hackers along the way? Well, it all comes down to the final step, the secure handshake.
I love this analogy, so let's stick with it. The IP address, that gets the data to the right building, the correct computer. But once the delivery person is inside the lobby, they need to know which apartment to go to. That's exactly what ports are. They are numbered doors for specific services on that computer. So for example, secure web traffic knows to knock on door number 443, while an email might go to a completely different door.
And the difference between a secure port and an unsecure one is huge. It's basically the difference between sending a postcard and sending a locked safe. Using old unsecure protocol like plain HTTP is like mailing a postcard. Anyone who intercepts it along the way can just read your message. But using modern secure protocols like HTTPS, well, that's like putting your message in a steel safe. It encrypts the data, turning it into complete gibberish for anyone who doesn't have the key. And really, that's the core of it. That's how the modern internet can function safely. The port acts like a traffic director, making sure the data gets to the right app. And the secure protocol acts like a bodyguard, wrapping that data in a layer of encryption to keep it safe the whole way there. And there you have it. From a simple click inside your house, on a journey across the entire global internet, to a secure handshake with the server halfway around the world, all happening in less time than it takes to blink. We've seen how all these amazing pieces are designed to work together, both seamlessly and securely. But that brings me to one final and I think crucial question for you. Now that you know all the different links in this incredible chain, what do you think is the weakest one in your own network?